Okay, welcome EGN 325. Okay, today we are going to grade our own exams. What? Why would I do that? What are we paying you for if I'm grading my own exam? Well, here's what I think. I think that this is a good learning experience. I think this gives you an opportunity to see where I was going with a problem, what I thought was the right answer, understand where you may not have quite followed that, and understand why. I think it's better. So, also, by the time, you'll see even when I get finished with this stuff, there's so many chicken scratches that, exactly where you put zeta equals 0.707 or whatever the answer was. And you say, hey, I put it there. But for me, I can't even look through your stuff to find it easily enough. I found that this is the best review, best way to review. Because now you have your own stuff, you're kind of having to give yourself a value judgment, and that's good. But just be forewarned here, I do look over the exam. So you're going to get your exam that you already did, and you're going to get a different color pen and go over it as we go along here. All right. What's the definition for settling time? That's how long it takes the system to stop moving at steady state. Oftentimes we say it's within 2% of the final value. That's the 4 tau criteria. Many times people use 1% of the final value, and that's 5 times the time constant gets you within 1%. Notice here that e to the minus at, it never settles. It never does settle. Right? It just keeps going closer and closer to the asymptotic end, and that's why we use the 2%. Okay, define system overshoot. How far the system moves past the steady state value before settling. Now, there's a formula for that. You could write that down. Percent overshoot is equal to the max minus the steady state value divided by steady state value times 100. You could even draw a picture of it if you wanted to, where this is the overshoot. Any of those are fine. Okay, list 4 reasons to use error feedback control in a system. Reduce the steady state error. Modify the system dynamics. Reduce the effects of parameter errors. And reduce the effects of disturbances. Okay, give an example of an open loop system. Open loop. I like coffee, so this is like a push button coffee grinder. Right? You just push the button, you got enough, unbush it. Okay. Closed loop system. I just said, the cruise control for a car. Right? You tell it the set point, it goes to the set point, and you're done with it. How can you tell if a system is stable in the S-plane? It's only stable if all the closed loop poles are in the left half plane. You can draw a picture if you'd like to here. That's bad. Good. Right? You can do that. Okay. What assumptions must be made to define a system transfer function. All right, a linear system, it has to be a linear system, but we haven't talked about that much, so if you didn't put that in. What you really need to know is that the transfer function is no initial conditions. It also has to be a single input, single output system. Actually, there's another piece of it. Again, those two I don't count. So if you didn't put those, that's all right too. All right, so let's see. We're all done here. Let's grade this. So let's see, there's 1, 2, 3, 4, 5, 6 questions. So that means they're 4 points apiece. You'll automatically get 1 whole point without doing anything. So there's 4 points for this one. So you want to say the time, how long does it take for the system to stop moving and then at steady state. You can put in this 2% thing if you want to. That's 4 tau, whatever you want. But if you talk about how long it takes and stop moving at steady state, give yourself 4 points. If you forgot one of those things, you can try and take off a point or something. Okay. For steady, how far the system moves past the steady state value before settling, right? So you want to say moves past the steady state value before settling. So you should say those 3 things. If you've given yourself those 3 things, 4 points. This one, 1, 2, 3, 4. I told you this was going to be on the exam, so you have to have all 4 of those things, or you don't get it. 2 each for closed loop. So remember that the open loop just is something you turn on and off, and the closed loop is something that has a sensor and tells you how far away you are from what you want to get to. Okay, that's 4 points there too. So what I want you to do too is give yourself a number of points and circle those number of points that you've given yourself. How can you tell if a system is stable in the S-plane? Only stable if all of the closed loop system, so you have to all of the closed loop poles are in the left half plane. So you have to have those two, all those things, all closed loop poles, left half plane. Any other things you can do, that's fine, that's 4 points. So for this one, really, you just have to say no initial conditions, you get those 4 points. Okay. All right. Then add them all up and give yourself 24. So put all the points up here for me too. Okay? Good. Let's go on to this next spot here. What we're going to do is we're going to look at this. Another pen here. Okay. So let's see. What is the problem 2? What is the characteristic equation? The characteristic equation here is S minus 7 equals 0. That means that S equals 7. Here. 1, 2, 3, 4, 5, 6, 7. I didn't put enough of them in here. S equals 7. You notice it's in the right half plane. That means it has a solution of form e to the plus at. That looks like this. Boom. That's a coronavirus infections. Right? Those are the coronavirus infections. Okay. So this next one's a little bit different. So that's why I didn't really care about this at all. I didn't even care about any of it. And, well, anyway, this one is a little different. So this one has S plus 7 equals 0. That means S equals minus 7. 1, 2, 3, 4, 5, 6, 7. Minus 7. S equals minus 7. And what we could do here, let's go back. Let's just go back and grade this one first. So, did you tell me where the roots of the characteristic equation is? Yes, you get 1 point. Did you draw the root of the characteristic equation? That's 2 points. Did you draw me a picture? That's 3 points for a total of 6 points for this one. Okay, so that means 1, 2, 3, 4, 6 times 4 is 24. So you already got 1 point up there. I'm giving away these points left and right. Okay, so here's, again, characteristic equation. We're drawing in the root of the characteristic equation. We know that this is a first-order system, so we really just have to sketch in a generic first-order system. We might want to put where the steady state is. The steady state is where t of s equals 0 is equal to 16 over 7. So we can just write 16 over 7. That's where that is. There's 1 times the time constant, which is equal to 1 over 7. That's the time constant. And that is 63% of the final value. 1 times the time constant, 2, 3, 4 times the time constant is the settling time. And so, you might want to write that in there. And so when you do all those things, again, 1 point for finding the root, 2 points for drawing it on here, and then 3 points over here. For these 3 points, you should put down the time constant, maybe 63%. You should have drawn this as the right direction. 16/7 with the settling time, with the steady state, and then the settling time. So here's 1, 2, 3, 4, 5 different things that you should be able to go. If you did 3 of those 5 things, give yourself 3 points. That's fine. All right. All right, so this one, I want to make sure that you understand on this one. This one is not in canonical form, so maybe the easiest thing to do is to put it in canonical form, 7/6s plus 36. So a lot of times I do that 36 stuff because even though I know that omega n is equal to 6 at that point in time. This is 2 zeta omega n is 7/6. It's about 1, so that means zeta omega n is equal to 1/2 7/6. I'm going to call that 1. I'm going to call that 7/12. I'm just going to call it 1/2. So I'm going to put it right here. About 1/2. So if that's about 1/2, then what we can do is, omega n and omega d, like this is so underdamped that this is 6 omega n is equal to 6, 1, 2, 3, 4, 5, 6. So it's not quite 6. Oops, I didn't put it quite in the right place. It's not quite 6. 1, 2, 3, 4, 5, 6. That's where those are. And then what we could do too, since omega n is, we can find out what zeta is equal to. 2 zeta is equal to 7/12, 1/6, about 0.1, damping ratio of 0.1. And with a damping ratio of 0.1 then, what we're going to do is we're just going to draw the response off of our little card. We might want to put where the steady state value is 35/216, right? If we're going to look at t of s equals 0. T of s equals 0, right? We can go all the way back here and just look at 35/216. That's fine. We might want to find out what the peak time is. TP is the generic tau p over omega n. We might want to put in like the envelope piece of it. E to the minus is zeta omega n t. We might want to put that in. We could put in the settling time here. T settling is 4/zeta omega n. T settling time, that's about 2 seconds when you plug that stuff in. And then we can also even put in here that the period is 2 pi over omega d, which is close enough to 2 pi over omega n for us to worry about. So we could do all those different things. And again here, did you find the roots of the characteristic equation? Yeah, if you found the roots of the characteristic equation, you get a point. Did you plot them? You get 2 points. If you once you drew this picture again, you got the steady state value. You could put in the peak time. You certainly wanted to put in the settling time. You could have put in the period and e to the zeta omega n. Some combination of those is another 3 points. So each one of these things is worth 6 points apiece, 6 points apiece, 6 points apiece. And then this final one here, let's see, s squared plus 100, s squared equals minus 100, s equals plus or minus I, 10. 2, 4, 6, 8, 10. Plus 10I, 2, 4, 6, 8, 10. Minus 10I. So those are the roots of the characteristic equation. So this one, the unit step input, with a zeta equals 0, you get 100% overshoot. The unit step part of it, it starts at 0. Its steady state value, since it's 100% overshoot, its steady state value is 5/100. And so again, here you have the t peak is tau peak over omega n. You might be able to find out what the period here is. Period is 2 pi over omega n. There's no settling time, no TS. It never settles, those sorts of things. So again, point for the 2 points for that, 2 points for that, and then the steady state value, the peak time, the period, no settling time. Any one of those three things is another 3 points. Okay? Here, and you should put in here that you got the first point easy, and then you got 24 points more. So I want you to put in your total up here for me. All right, now we've got this next problem we're going to try and do here. It says, experimental data was taken. In each one, the input is a step voltage of 1 and the output is the angle, theta. Determine the transfer function for each system. So here, I can definitely see that because this has overshoot, it's oscillatory, you know, I'm going to try and make this look like a second order system. I think it looks pretty much like a second order system. We'll talk about higher order systems as we go along. So this is e to the minus zeta omega n t is that envelope that you might put in there. You might want to look and see what the steady state is. So the steady state is equal to 0.37, let's say, something like that. I should have probably gotten more even numbers for that. So what we might want to look at is we might want to just look at the, here's the peak time, T peak. But before we look at that, we might want to look at what the percent overshoot is. The percent overshoot is going to be, I'm going to call that 0.65 minus 0.37 divided by 0.37 times 100. Percent overshoot is about 75%. We know enough now that that's pretty much telling us that zeta equals 0.1, about zeta equals 0.1. You know, and so we can look and see where the settling time is. TS is equal to 4 over zeta omega n. And so if that's 4 over zeta omega n, that's going to be 4 over, yep, I'm sorry, 0.4. This peak, maybe this is an easiest way to tell. The peak time is going to be tau peak over omega n. We haven't figured out omega n yet. Let's figure out where we're going to get omega n. Well, I calculated omega n this way. 1, 2, 3, 4, 5 cycles. 5 cycles in 0.4. Oh, no, that's 0.35 minus this one where it starts is 0.03. That's 15 cycles per second. That's going to tell me that omega n is going to be 15 times 2 pi. It's about 94 radians per second. Technically, we should carry along all of our stuff that way. We could also look at settling time as 4 over zeta omega n. Once we know what zeta is, this will also tell us omega n. Let's see what this one says. Omega n is going to be 4 over 0.4, 1 over 0.1. So we could have, this is one way to do it, and this is another way to do it. So 4 over 0.4 is 10, over 0.1 is about 100 radians per second. So, okay, you know, 100 or 94, either one of those is all right. So since we know that this looks like a second order system, this second order system is theta over volts, and that's going to be the constant times omega n squared over s squared plus 2 zeta omega n s plus omega n squared. And basically, you know, that's really, you can plug in numbers if you want to, but here, look, you've told me what omega n is. You've told me what the constant is. And you told me what zeta is. Where did we do that? And you told me what zeta is. So really, that's all you have to do. And what I'm going to do is I'm going to say for each one of these pieces, like there's 3 points for this one, 3 points for showing me the general form of the second order response, 3 points for finding like the natural frequency, 3 points for the damping ratio, 3 more points for that. So 1, 2, 3, 6, 9, 1, 2, 3, 4, that's 12 points. There you go. For a total of 12 points, right? Oh, you already get +1? Holy cow. All right. So now let's look at this next one. The next one's a little bit, so when they're under damped like this, you just kind of have to fudge in the e to the minus zeta omega n t term pretty much like that. You might go look at the peak time, but you also might look at the percent overshoot, which is the percent overshoot is going to be 700 and let's call 730 minus 700 over 700 times 100. That's about 5% overshoot. 5% overshoot corresponds to zeta equals 0.707. So now we're good with that. We can figure out what the peak time is. Peak time is about tau peak over omega n. Let's see, here we go. Let's look at settling time is going to be 2.5 seconds. That's a 4 over zeta omega n. Since we know what zeta and omega n is, we're going to say omega n is going to be 4 over 0.707, 1 over 2.5. That's about 2.2 seconds, 2.2 radians per second. And then if we want to look at the peak time, this is going to be 3.14, right? Even though it's heavily damped, if you look real close, the peak time on your generic thing might not quite be 3.14, but, it's close enough. And then omega n is about 2.2. That's about, peak time. Oh, we already know what the peak time is. We could have figured out omega n from that too. It's about 1.5 seconds, something like that. All right, so once again, what I asked you to do is get the transfer function, theta over v, and that's going to be some constant times omega n squared over s squared plus 2 zeta omega n s plus omega n squared. And then where the constant is, and it turns out the constant equals the steady state value, which is equal to 700. So once again, we're going to try and grade that. Here's 3 points for this, 3 points for zeta, 3 points for omega n, and 3 points for that constant, for a total of 12 points. And again, I want you to go back over here, put in your +1, 24, you're almost there. All right. Now the last one is a lot harder. This is, I know these are hard. This last one is a hard one. I sometimes wonder if I should be putting these things in or not. I never can tell for sure, but put it in I did. So let's see what we got here. So given the system shown, C equals 12, tau equals 1/20, design a control system to point the output angle theta to some desired value. Sketch the response to a step input for the final system that you design. Hint number 1, watch out. That motor block diagram is not in canonical form. Hint number 2, use the root locus method for the controlled design. So, oh, did somebody say we have to design a controller here? Well, I know how to do this. I know how to design controllers. There. That's the controller. And now I also recognize what the open loop system looks like. Here, let's put that around. I also recognize what the open loop system looks like. This is GH of S. In the book, that's what they call it. So KGH. So I'm going to write this differently. KPGH is equal to KP C tau S plus 1 over S. Now, that's not in canonical form, so I'm going to change it to canonical form. This is s plus 1 over tau, and this is 1 over s plus 0. So this emphasizes what the roots of the characteristic equation are. Plus, I want to emphasize that tau s plus 1 is not the same as s plus 1 over tau. The magnitudes are definitely different. The roots are the same, but the magnitudes of those are too different. And so what I'm going to do is I'm going to use the the magnitude criteria. It says Kp GH equals minus 1. That means that Kp is equal to 1 over the magnitude of GH, and that 1 over the magnitude of GH is the magnitude of s plus 0, magnitude of s plus 1 over tau, and then it's divided by C is 12, and 1 over tau is 20, so C times 20. And so if I go, I don't know how big to make these things. Like, there's an algebraic way of doing this too, but I wanted you to use the root locus method. That's why I gave you the hint, and I think you'll see why I asked you to do it this way later. I'm just going to put it in here. So I'm going to call this a 1, 2, 3, 4, 5. 5, 10, 15. I might have made this too big. 20. Let's just, okay, this is minus 20. I used up the whole page. I'm going to fudge this one a little bit. Okay, I'll fudge this a little bit. That's okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 5. Okay, so I'm just, you can get a ruler and measure this stuff, and it gets pretty good. But even by hand, that's okay. So let's see, where are the closed loop poles? So I know that the root locus starts at the closed loop poles. That's at s equals 0 and s equals minus 20. So those are the closed loop poles. I can look and see where real axis segments are. So I'm going to drop real axis segments. So to the left of odd number of poles and 0. No, 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 no. Yep. Yes. And then if I could go on that way, no. So those are the real axis segments. So then I want to say, like, I wonder how many asymptotes there are. And what I can do is I can say that the number of asymptotes is equal to the number of poles minus the number of finite zeros, which in this case is 2. The 2 of them, if you plug that into the formula, it's plus or minus 90 degrees. Now, I don't know where the asymptotes hit the real axis, but that is the sum of the poles minus the sum of the zeros over the number of finite poles minus the number of finite zeros. And so in this case, that's going to be, now, for a second order system, this always works this way. It's the sum of the poles is minus 20 minus 0 over 2 equals 10. It just happens that it's right halfway in, minus 10. This is equals sigma asymptote. So that means that the asymptotes, infinite asymptotes, go up and they go down, right? So anywhere on these lines, this is the root locus for this system. You can do it anywhere on this line, right? Do it anywhere on this line. And then what we want to do is say, well, where on this line is a good place? Anywhere makes it stable, but a lot of times, again, I've said, suppose I just want to do, I want to do a zeta equals 0.707. That means theta equals 45 degrees. And that means I'm going to choose this as my desired root location. Okay, so now the last thing I have to do is find out what the gain is. Here, I've already got the equation for gain, Kp equals magnitude of s plus 0, magnitude of s plus 1 over tau, divided by 240. So let's just go see what the magnitude of s plus 0 looks like. This is the vector s plus 20. This is the vector s plus 0. Now, I can just do the math. Look, this is 10 and this is 10. So the magnitude of s plus 0 is equal to the square root of 10 squared plus 10 squared. Square root, that's going to be 14. 1.707. So if I just put those in, this is going to be 14, 14, and this is 220, 240, sorry, 240. And then that's just going to be, if you go look at what KP is, KP equals 0. I don't know, it's something like 0.83. Now what does that look like? Response? The response? Well, we already know what this looks like because we just put it in. We just drew it. We just drew it in. Here's time. It's got about 5% overshoot because that's the zeta we picked. We can look and see where T settling is. TS is equal to 4 over zeta omega n. Let's see, so what is, oh, I guess we do have to do the closed loop transfer function T of S is equal to Kp C over tau divided by S squared plus 1 over tau S plus Kp C over tau. So that means omega n squared is equal to 0.83 times 12 times 20. That's about 200. Oh, so omega n is 14. What we already figured out what omega n was, 14. And so 4 over zeta omega n is, you know, it's something like 10 seconds. So that's the response. All right. So now comes the hard part, is that the management team guy, he just went out and bought a new sensor. And this sensor is much, much slower. And so what I'm going to tell you that if you knew how to do this, again, this is kind of a thing that you kind of need to know what to do here. So let's now look at what first of all, it says, hey, draw this picture in here. Draw this picture of what that sensor looks like. That sensor looks like this. It's a first order system. It has a steady state gain of 1. Tau is equal to 1 second, 2, 3, 4. That means it settles in 4 seconds. Right? So there's a response. And now what we'll do is we'll look at what the new KP GH is equal to. The new KP GH is going to be C over tau, S plus 1 over tau, and then this is going to be 1 over S plus 0. So we have, those are all the same, but now we've added something here, 1 over S plus 1. We have a new root there. So we have the let's plot that root this time. Here we can plot it right here at S equals 1. I'm adding this in. S equals 1. And so how many asymptotes do we have? Number of asymptotes is equal to the number of poles minus the number of zeros, which is going to be 1, 2, 3 minus 0 is 3 asymptotes. The 3 asymptotes gives you plus or minus 60 degrees and then 1 at 180 degrees. So if I just really quickly, here. Where is the asymptote? Sigma asymptote. Where does it hit? So I know it's plus or minus 60 degrees, but where does it hit? It's the sum of the poles minus the sum of the zeros divided by the number of finite poles minus the number of finite zeros. That's going to be, the sum of the poles is minus 20 minus 1 plus 0 over 3. 21 divided by 3 is 7. 5, 6, 7. Here's sigma asymptote now. And, you know, I could get out my protractor, but I know they're plus or minus 60 degrees, right? Plus or minus 60. And the other one's at 180, so it's just going out that way. Going out that way. And then I can also look at real axis segments. So let's see. This is a real axis segment, but no more real axis segments. And then this is a real axis segment going out that way. Is the real axis segment. So somewhere in here, these two break away. And they have to go up, and eventually they have to get asymptotically approach the asymptotes. Now, where does that happen? When you're doing these sketches, you can't tell exactly where they are. But we might say that maybe it crosses at 4. Let's say it crosses at 4. And so now, if it crosses at 4, why don't we use it? So then it says, find the gain where the roots are on the imaginary axis. So we're going to find the gain where the roots are on the imaginary axis. So what I'm going to do is I'm going to draw this root here. That's s plus 0. I'm going to draw this root. This is s plus 1. And then I'm going to draw this root. S plus 20. Right? Now, how big is s plus 0? Oh, let's figure out what the Kp is. Kp is equal to 1 over GH, which is going to be s plus 20, magnitude of s plus 20, magnitude of s plus 0, and the magnitude of s plus 1, all over 212 times 20, 240. So, how big is s plus 0? I would say it's 4. How big is s plus 1? Oh, it's 4 too. How big is s plus 20? Oh, it's about 20. So this is about 20 times 8. 4 times 4 is 16. Sorry, 4 times 20 times 8. 16 times 20 is about 320 over 240. I'm just going to say it's about 1. It's a little bigger than 1, but it's about 1. So that means that when you designed your system the first time with a gain of 0.83, and then somebody from the management team bought a new sensor and put it in, they moved the root locus with that sensor. They changed the dynamics of your system so that it was almost unstable. So at that point, it's just marginally stable. All right, so let's see how the heck are we going to grade this thing. So did you put this closed loop system in here where I said design a control system? Did you do that? 5 points. Did you find the gain that you needed? Either find the gain so you could do it this way or algebraically. Either way, that's 5 points. Up to 5 points. So if you didn't get exactly the right answer, but you did the right process, you might take off a point. So if you drew the root locus, that means you had to figure out where the asymptotes were, where the real axis segments. So for the root locus, that's another 5 points. And then I did ask you to do this, so if you just did this one, that's another 5 points. And then all the rest of this other stuff, that's up to 5 points for that. And you can get all those points. Okay, so that's 25 points. Then go back, make sure you go back here, put your 25 points in here, total up the score and circle it for me. Now, I am going to insist that you PDF this. I will put a place on Blackbeard for you to put the PDF document and that sort of thing. Okay?